our goal for today is to talk about an idea. We already know that exponential functions are wonderful for solving differential equations. They're our favorite kind. But can they do even more for us? What do I mean? Well, remember, if we go back to one of the very first topics we had in the course, we could look at a very simple differential equation. X prime equals ax, where a is a number, and this was the exponential model. And maybe we had an initial condition, x of 0. Well, we can solve that, and we did. And the solution is e to the at times x of 0. Okay, now let's come to our setting. Our setting is our a is not a number, a matrix. We're talking about systems. So x prime equals matrix A times x. We have some initial conditions as well, x of 0. It would be nice if we could say, oh, our solution would be e to the at x of 0. In other words, that there was some nice symmetry. Now, is that possible? Is it true? And by the end of today, we hope that we will become convinced, yes. But of course the question is, what is e to the at? How do we find it? What does it mean? And how can we compute it? So let's start with a nice observation, which is going to be very useful. And that is to say, when we multiply a matrix times a vector, so we have A matrix, vector B, what does it mean? Well, the claim is that this can be thought of as taking a linear combination of the columns. You know, channel your inner Lord of the Rings character, column, column. So how do we see this? Well, here's an example. So we have a 3 by 3 matrix, and we have a vector. Now, if we carried out matrix multiplication, following our traditional rules, well, we'd be going along the first row, and what would we have? Well, we'd have B1, A11, and then plus B2, A12, plus B3, A13, and similar for the other rows. And so we carry that out. Okay, that's great. But then what can we do? Well, what we can do is we can say, look, matrices, and this is a vector is a matrix, really work well with addition. And so we can combine things. And when you can combine, you can also separate, pull things apart. Whoops, I forgot to put down a number here. A2, 3. There we go, A3, 3. So what we'll do is we'll separate using our addition into 3 pieces. So we say, okay, hey, this is the same as B1, A11, B1, A21, B1, A31, plus, and then the middle piece, B2, A12, B2, A22, B2, A32, and our last piece. All right, now, at this point, we say, great, wonderful. We've used the fact that we can break up over addition. The other thing we can do is pull out factors, scaling, right? So pull out the B1, you'll be left with B1, A11, A21, A31. Here, pull out the B2, you'll have A12, A22, A32. Pull out the B3, you'll have A13, A23, A33. So indeed, this is correct. And so, again, key idea. If we take matrix times vector, we can think of it as combining the columns in some linear way. And more particularly, thinking about our terminology, we could say, oh, this looks like a superposition of the columns. Right? Because what is superposition? It says, well, what we do is we take a constants and addition and we combine them together. And now we're ready to sort of delve into the nice idea. So here we go. Suppose we have our differential equation x prime equals ax, and we found our solutions. Now, when we talk about finding solutions, we mean a collection of linearly independent solutions where we get all solutions by our superposition. So we'll call these x1 through xn. Normally, by the way, we're only going to do n equals 2, but we're just stating things in general for now. Then what we're going to do is we're going to introduce a new matrix, and it's going to be a fundamental matrix. And so that's what its name is. That's what we call it, a fundamental matrix. Now, I want to point out a really important key word here, which is the word And we'll come back to why we say Now, how does this work? Well, what you do is you take the solutions and you put them in as the columns of this vector. Sorry, the columns of this matrix. And we're going to call this phi of t. All right, so here's our fundamental matrix. So we've packed all our solutions in. All right, great. Now, why do we use the word Well, because there are choices that we could have made. For example, we could have rearranged the columns in a different order. Or maybe we have our solutions represented slightly differently. Maybe we scaled x2 by a factor of 2 versus what somebody else did. So phi of t is not unique. There are many possibilities. So that's why we use the word And by the way, we've seen this matrix before. It's the same matrix that we used when we talked about the Wronskian. And we said, okay, the Wronskian says, take the solutions, take the determinant. Here we're just saying, take the solutions, but leave it as a matrix, no determinant. So that's the difference now. Now, what were we caring about with the Wronskian? Well, the Wronskian, we said we want that to be non-zero. Well, if we think back about things we said about determinants, having a determinant not zero means that we can take inverses. And so that's the key idea. So when the Wronskian is non-zero, you can find the inverse. And in particular, if the Wronskian is non-zero for all t, then we can always find the inverse. Okay, so here we go. Our nice, beautiful fact. If we have our solution x prime equals ax, and we have our initial conditions x of 0, then our solution looks like phi of t, phi 0 inverse x0. All right. And now if you think back to what we wanted, we said, oh, well, we wanted something. This should be looking like e to the at x0. So that's why we're going to say, all right, idea. We're going to say that phi of t, phi 0 inverse, we're going to call that our e to the at. And you might say, that seems like kind of cheating. It does what you think it should do. Is that justified? Yes. Hold on. We will justify that by the end of today. All right. So first off, why is this fact true? Okay, so how do we know it? Well, we should actually check a couple things. One, is it a solution? Two, is it a solution satisfying the initial conditions? Let's actually start with the second thing first. So let's check that the initial conditions are satisfied. All right. So how do you do that? Well, what do we know? We know when we plug in t equals 0, we should get x of 0. Okay, so let's plug that in. So x of 0, does that equal? Well, let's find out. We have phi of 0, phi 0 inverse x0. So the only place where t shows up is right there. Now notice what we have. Phi of 0, phi 0 inverse. What happens when you multiply a matrix times its inverse? What do you get? You get the identity. They're sort of undoing each other. So we say, oh, well, this part acts like the identity. It acts like 1. And we say, well, great. If I take I times x of 0, then, hey, that is x of 0. So, success. We verified initial conditions. Okay, so the initial conditions are satisfied. But why is it a solution? Okay, so now to understand why it's a solution, we think about what's going on. So first off, we'll say we have our x of t is written as phi of t, and then we have this phi 0 inverse x 0. I'm going to call this a vector. Let's call this c1 down to cn. And now, phi, what does that look like? Well, it's up here. It's a matrix where the columns are solutions. And so, when we say, okay, we have matrix times vector, then, according to what we talked about, what we get is C1 times the first column, C2 times the second column, all the way to Cn times the last column. In other words, what we have is that this is a superposition of solutions. And, well, if you take a superposition of solutions, it's a solution. So that's the other thing we had to check. So it satisfies the initial conditions, and it's a solution. And so we're done. Great. Brilliant. Brilliant. All right. So, good. Now, there's some questions here. Let's think about this. Does phi of t depend on how we represent our solutions? For example, the ordering of the columns. And we've already talked about that, and the answer is yes, it does. That's why we have to use the word Okay, great. What about e to the at? Does that depend on how we choose phi of t? Okay, so now that's a little bit more interesting, because e to the at is not the same as phi of t. There's this little extra piece. All right, so the answer to the first question, by the way, yes. What about the second question? Does e to the at depend on which fundamental matrix we pick to use? The answer is no. E to the at will always be the same. So no matter which fundamental matrix you use, as long as it's a full set of linearly independent solutions, it will always produce the same e to the at. Now you might wonder, how? How does that work? Well, the answer is this phi 0 inverse essentially puts things all in the right order. And so that's how it corrects. But you might say, but still, why? What's going on? What's this magical property that guarantees it's always going to be the same? And here's the answer. It comes down to one word, and it's a long word. It's called uniqueness. Because solutions are unique. So in other words, if I give you a set of initial values and a differential equation, and I'm told that there's a unique solution, then that means there's only one possibility. Okay, so what can I do? Well, what I can do is I can say, all right, let's make my initial value, put a 1 in the first entry and zeros everywhere else. And now, if I times that by this expression, well, there's only one answer. So that says, okay, I'm always going to get the same first column. Okay, what if I put a 0, 1 in the rest 0? Again, there's a unique answer. So this will always have the same second column, and so forth and so on. So it's always going to agree. So here's a nice comment to make. E to the at is the fundamental matrix. In other words, it's the best one. So if you're asked to find a fundamental matrix, and you can find any, but if you're asked to find the best one, it's e to the at. Because e to the at has this extra nice property, namely that our solution looks like x of t equals e to the at x of 0. Because it's so nice. It's the preferred one to have. All right, good. So now let's take a look at an example. We're given x prime is this matrix 5, minus 4, 3, minus 2x. And we're asked to find 5t phi 0 inverse. As a reminder, This is what we're calling e to the at. Now we're just putting that as a side note. And then we're told, use this to find the solution with x of 0 equals 7, negative 5. All right, so here we go. Now, what do we need? Well, we're forming a fundamental matrix. The fundamental matrix, the columns are solutions. So we have to find the solutions. So we're doing the same process as we've always done. We start by taking our matrix and finding eigenvalues. All right, so step 1, find eigenvalues. And, well, you'll get used to this. You know, it's always like, what do we do? How about we find eigenvalues? Brilliant! And off we go. Okay, so we're going to have the determinant 5 minus lambda minus 4, 3, minus 2 minus lambda. So remember, this is our a minus lambda I. So we have 5 minus lambda minus 2 minus lambda, subtract 3 times minus 4. All right, well, that'll be minus 10 minus 5 lambda plus 2 lambda plus lambda squared. And this will be a plus 12. Rearranging that makes a lambda squared. Minus 5 plus 2 makes minus 3 lambda. Minus 10 plus 12 makes a plus 2. All right, does that factor? Yes, yes. We will be nice and we'll give you things that look nice, things that factor. Lambda minus 1, lambda minus 2 equals 0. And so our eigenvalues are 1 and 2. All right, good, good. Okay, so lambda equals 1, 2. Now, what comes next? Well, now that we have eigenvalues, next up, eigenvectors. All right, and we have to find 2 of them. One for lambda equals 1, one for lambda equals 2. So let's start with 1. Why not? Okay, so here we go. Find our eigenvectors. And we'll start with lambda equals 1. So we're going to take a minus 1 times I. So that would be the matrix 4 minus 4, 3 minus 3. And we're looking for some vector so that when we multiply we get 0 or 0. Can we think of a vector that does this? Any vector that does this will work. Can we think of one that actually does this? Well, you can, of course, use rows, but you can eyeball and say, wait a second, 1, 1 does this really well. So we say, great, our eigenvector. We just found it. Okay, well, that's for lambda equals 1. Now, we're going to do the same thing, lambda equals 2. So, think about a minus 2i. So that would be 3 minus 4, 3, and minus 4. All right, great. Well, can we think of any vector that does that? Maybe this isn't so quick as the 1, 1. And when I say it does that, I should say when we multiply, we get 0, 0. Well, but again, we can always do our trick. Pick a row, doesn't matter which one, write it backwards, minus 4, 3, and flip a sign. 4, 3, great, done. So that's also our eigenvector. All right, so now we have our 2 eigenvectors, our eigenvalues, so we have our solutions. So wonderful! What does that mean? Well, it means we can talk about what our solutions look like. So we have our x1. Well, that's going to be, well, let's do lambda equals 1. So that's e to the eigenvalue t, 1 times t, times eigenvector, 1, 1. And then x2, we'll do with lambda equals 2, e to the eigenvalue t, 2t, times eigenvector, 4, 3. All right, good. Now we put this into our fundamental matrix. So phi of t, what does that look like? Well, we'll put in our first column is our first solution. E to the t, e to the t. Second column, second solution. 4e to the 2t, 3e to the 2t. All right, good. Now, what are we after? We're after phi of t, phi 0 inverse. Okay, so let's find phi of 0. Well, e to 0 is 1, so that's 1, 1, 4, 3. There we go. Phi 0 inverse, well, that would be, we have our nice rule for that, 1 over the determinant, 3 minus 4. And how does it work? Well, we swap the entries on the diagonal, so we'll have a 3, 1, and then off the diagonal, we change the signs, minus 1, minus 4. All right, good. Now, by the way, 1 over 3 minus 4 is 1 over negative 1. So there's a negative sign in the front. So we can push the negative in, and we'll get minus 3, 4, 1, minus 1. All right, so here we go. We've got phi. We've got phi 0 inverse. So we're really close. What do we need to do? We need to multiply these matrices together. So again, this is e to the at, which is phi of t, phi 0 inverse. So e to the t, 4e to the 2t, e to the t, 3e to the 2t, times minus 3, 4, 1, minus 1. All right? And now multiply. So minus 3 e to the t plus 4 e to the 2t. All right, now we'll go to the first row, second column. We'll have 4 e to the t, subtract 4 e to the 2t. Now, second row, first column, minus 3 e to the t plus 3 e to the 2t. And finally, second row, second column, 4 e to the t, subtract 3 e to the 2t. And there we go. Good, good. Now, we're done, right? Well, we're done with the first part. There's a second part. Use this to find the solution with initial conditions, x of 0 equals 7 minus 5. Now, previously we would say, oh, we're going to have some constant x1 plus some constant x2. We're going to solve for the constants and, set up equations and work it out. We're not going to do that. We don't have to do that. The machinery is in place that carries out that computation automatically. So all the work that we've been doing before, it's saying, hey, I'll do it for you. As long as you give me this phi t, phi 0 inverse, or if you like, e to the at, I'm happy. So what's the answer? Well, what we do is we say, all right, we take our phi of t times our phi 0 inverse, again, that's e to the at, and we multiply it by x0. Now, I'm going to pause here to say we have two options. Namely, we can use what we already have, which is great, times this by x0, or we can be a little bit step back and say, here's another way to think about it. Now, when we're doing this computation here, we have three things multiplying. We can multiply the first two together and then multiply by the x0. That works great. Or, hear me out, we can multiply the last two together and then multiply by phi of t. You'll get the same answer either way. Now, why might we prefer multiplying the last two together? Well, the nice thing is here, these are all numbers in both pieces. Phi 0 inverse x 0, number, 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 number. And so that makes it a little bit easier to carry out the multiplication. And so I'm going to do that. So you don't have to. I'm just wanted to point out it's a possibility. Okay, so we have 5t. I'm just going to abbreviate this as 5t for right now. We have our phi 0 inverse, minus 3, 4, 1, minus 1. And then we have times 7, negative 5. And, okay, so that's phi of t. And, all right, what do we have? We have minus 21 minus 20. Okay, minus 41. Then we have 7 plus 5, 12. All right, so now we say, okay, that leaves us with our computation e to the t, 4e to the 2t, e to the t, 3e to the 2t, times negative 41 and 12. All right, well, that leaves us with, carrying that out, we have minus 41 e to the t plus 48 e to the 2t, right? And then minus 41 e to the t and plus 36 e to the 2t. And we're done. We're done. Good. And so the reason I did this is just numbers with numbers is easier than functions with numbers. So to do as much number computation, it gets you, makes life simpler. And don't we want life to be simple? I do. I hope you do too. So far we called what we wanted e to the at because we said, well, it's doing the thing we want, so we might as well give it the name that corresponds to that thing. But is there another way to talk about computing e to the at, something that makes sense, that we can say, oh yeah, I can get behind that? The answer is yes. We say, okay, what do we have? Well, it turns out that there's a few things we can do with matrices really well. We can scale matrices, we can multiply them, we can add them. Now, when you think about those operations, scale, multiply, add, that's like polynomials. And polynomials, you can do a lot with polynomials. And in particular, we have this great aha, which is right here, the great aha, which says, wait a second, the exponential function, we can do that by computing a polynomial. In particular, we have the Taylor series, I know, flashback, which says, hey, e to the z is this big long polynomial, 1 plus z plus 1 over 2 factorial z squared, and da-da-da-da-da. So now, we say, okay, look, what were we doing? Previously, we were plugging in our z. So now, idea. Let's not plug in z, let's plug in a times t, right? Because it's sort of like we have our machine, and our machine says you plug in z, and this is e to the z. And we say, great, machine, here you go, I'm plugging in a times t. And the machine says, all right, whatever, and I'll run it through the process. Now, how does it work? Well, wherever you see a z, I'm going to put a times t, which, by the way, is the same as t times a, and so forth and so on. Now, there's one small subtlety, the 1. Well, the 1 is going to be replaced by I. Now, you might say, wait, how did that happen? Well, the best way to think about it is that this one here really is z to the 0. So when we think of this I, we're thinking about a to the 0 power. And a to the 0 power we think of as the identity. So that's why we put an I. So we say, great. So again, it's very similar. So all we have to do, is just compute that, and we have e to the at. So let's think about how we can start going about doing that. So to get us going, we have an example. Suppose we have this matrix, and it kind of looks like an A, doesn't it? But it's actually a capital lambda. And there's a reason we picked that. And it's a diagonal matrix, meaning that the only entries we care about are on the diagonal, and off the diagonal you have zeros. And you have A, B. And the question is, well, compute E lambda t. All right. Well, what do we know? Well, we know that according to the rule we just had, that E lambda t, well, that's the identity plus t lambda plus t squared over 2 factorial lambda squared, and so forth and so on. All right. So what we need to do is say, well, what's happening with these lambdas when we multiply them together? All right. So we already know what lambda looks like. What about lambda lambda? Okay, so this is A0, 0, B times A0, 0, B. All right. So we'd have A squared 0. So that's A squared. And then 0, 0. Good, 0. And then 0, 0. Yeah, that's great. And then 0, B squared. Oh, well, that's kind of nice. So this is our lambda squared. How about lambda cubed, which we can think of as lambda squared lambda? So that's A squared, 0, 0, B squared times A 0, 0, B. Well, okay, that's A cubed 0, A cubed, and then we have 0, 0, 0, and we have 0, 0, 0, then we have 0, B squared B, B cubed. Oh, look at the pattern. For lambda, we get A and B. Lambda squared, A squared, B squared. Lambda cubed, A cubed, B cubed. Does it continue? The answer is yeah. Indeed it does. So that in general, we have lambda to the power k is A to the k, 0, 0, B to the k. Now, true story. When it comes to multiplying matrices, diagonal matrices are our favorite to multiply. Because if you take a diagonal matrix times a diagonal matrix, the only thing you have to do is multiply on the diagonal entries. And so it's very easy to multiply diagonal matrices together, and it's also easy to take powers of diagonal matrices. So where does this leave us? Well, let's now put it in. We say, okay, so what do we have? Well, we have E lambda t is the identity 1, 0, 0, 1 plus t A 0, 0, b plus t squared over 2 factorial A squared 0, 0, b squared plus t cubed over 3 factorial A cubed 0, 0, b cubed, and so forth. Now, push it into a single matrix, and what do we get? Well, we get 1 plus, and here we'll have a t plus, here we'll have t squared a squared, which we can write this as a t squared over 2 factorial. T cubed a cubed, again, we can write that as a t cubed over 3 factorial, and so forth. 0, 0. And now, in the bottom corner, right, why do we put zeros? Because they're all zeros, and they're all zeros in the off diagonals. In the bottom corner, again, we get 1 plus, here we'll have t times b plus t squared b squared is t times b squared over 2 factorial. T cubed times b cubed is t times b cubed over 3 factorial, and so forth. Now, well, the zeros are easy. They're going to be zeros. Do we recognize 1 plus at plus at squared over 2 factorial plus at cubed over 3 factorial? We do. It's the exponential function. In the Taylor series, it's e to the at. What about this lower right term? Similar, except instead of a, we have b. All right, cool. So it turned out that when we had a diagonal matrix, it it's very easy to compute e to that diagonal matrix times t. It's take e to the diagonal entries t, right? We had a, became e to at. Then we had b, e to bt. So diagonal matrices are easy. It would be nice if everything looked like a diagonal matrix. And it turns out that when we have a complete set of eigenvectors, there is a justified way to say it does look like a diagonal matrix. And in particular, the diagonal matrix it looks like is the diagonal matrix which has the eigenvalues on the diagonal. So what do we have? Well, again, we have our eigenvalues with eigenvectors, and a times the ith eigenvector is the ith eigenvalue times the ith eigenvector. Okay, so here's what you do. You take your matrix B and you throw in your eigenvectors. Then, the claim. It turns out that A is equal to your matrix B, your diagonal matrix with your eigenvalues, we'll call this capital lambda, and B inverse. Okay, so why is this true? Well, here's sort of a check. What are we going to do? Well, we're going to look at, take A times B and look at the kth column. So this EK says you're a column vector, which is a bunch of zeros, a 1, and a bunch of zeros. And so when you multiply a kth column, EK I should say, by a matrix, you're grabbing the kth column. So, okay, B times EK, you grab the kth column. Well, that's the kth column here. That's your VK, your kth eigenvector. And you say, okay, well, A times VK, well, since it's an eigenvector, we have our relationship. That's lambda k VK. All right, great. Well, now we can do the same thing here. We say, okay, take B times lambda times EK. Now, again, we're grabbing the kth column. When you grab the kth column here, it looks almost like what you have before with the EK. It's just a bunch of zeros, lambda k, and a bunch of zeros. So you say, oh, that's lambda k EK. You say, okay, lambda k, that's a scalar. And you say, all right, now grab the kth column of B. Well, again, that's VK. So, what do we have? We have that A times B equals B times lambda. All right, now what can you do? Well, we can say that A is A times B times B inverse. Why can we say that? What's B times B inverse? The identity, 1. Say, okay, well, great, that's true. And then we say, well, AB is B lambda, so we get B lambda B inverse. All right, now that's the justification. You don't need to remember that. The thing to remember is that when we have a full set of eigenvectors, we look like a diagonal matrix. We just have to have a B and a B inverse on the end, where B is your eigenvectors. So following up, what can we say? Well, now if you take A to the power of K, so we have K copies of this alternative way to write A, right? B eigenvalues, B inverse. Well, notice how you have these B inverse B's going along. What happens when you take B inverse times B? Well, what happens is you get a bunch of I's, right? They're acting like 1s. So they all go away, and then you have B's, then you get your lambdas showing up, and then there's a B inverse on the end. So how many lambdas are there? There's K of them. You say, oh, well, we know how to take lambda to the kth power, because we talked about before, diagonal entries are easy to raise to the kth power, and so, lo and behold, we get our matrix B, lambda 1 to the k, lambda 2 to the k, so forth and so on, down to lambda n to the k, B inverse. Now, throw that into e to the at, and you just carry it out, the computation, and you should do it once in your life. I don't know if this is your time to do it, but if you go through, you say, well, we know how to handle a to the power of k. We get a bunch of b's at the start. We get a bunch of b inverses on the end. So we pull them out. We have b and b inverse. And then we say, well, the stuff in the middle is stuff we know how to handle, because things are nice for diagonal matrices. And so we say, hey, we know what's going on. So that is our exponential. So that's great. We know how to find e to the at for a matrix, which is nice. Let's pause for a second here. We'll probably say this again, but I want to say it now. Suppose we look at this part right here. What is this? Well, if you carry out the computation, what you'll see is that the first part will look like the following. Now remember, B was our set of eigenvectors, and what you'll get is you'll get e lambda 1t times the first column of x, and then the second column will be e lambda 2t times the second column of x, and so forth and so on, down to e lambda nt times the nth column of x. Have we talked about this before? Sometime today. Have we seen this before? We have. This part is what we've been calling phi of t. They might say, ooh, well, what would happen if we plugged in t equals 0? Now, notice, come back here, what would happen? Well, there's no t inside this part. This is just numbers inside b. So when you plug in t equals 0, e to 0 is 1. And so you say, oh, so you have like b times identity, which means that this is b. So what does that say? Well, that says, whoops, quiet. What does that say? That says this b inverse here is what? It's phi 0 inverse. So we have it. We have our phi of t times our phi 0 inverse. Exactly what we want. Nice! So we really are justified in saying that phi of t, phi 0 inverse, is indeed e to the at. So okay, so it's not just because we'd like it to be that way, it's because it is that way. Cool. Let's turn to look at the repeated eigenvalue case. Now there's going to be two useful facts for us. And namely, it says, hey, for any value lambda, if you want to compute e to the power at, that's the same as e to the lambda t, e to the a minus lambda it. This can be shown by showing that certain properties of matrix exponentials hold, namely if a and b commute, so a times b equals b times a, then e to the a times e to the b is e to the a plus b. All right, so we'll skip the details. It's a fun exercise. Second fact, if we have a 2 by 2 matrix and we have repeated eigenvalues, then a minus lambda I squared is the 0 matrix. Okay, now compute e to the at. Well, we say, hey, if I want e to the at, for our first fact, we have e to the lambda t, e to the a minus lambda it. And now we say, well, how do we compute e to the a minus lambda it? Well, we have our definition in terms of that Taylor series. So we have the identity plus a minus lambda I t plus, and now we pull out our second fact. You see, the next thing that's going to happen is we're going to have a minus lambda I squared, but that's the 0 matrix. What about the next thing? We'd have a minus lambda I cubed. But to get to a minus lambda I cubed, you first get to a minus lambda I squared, and now we're all zeros, and then, okay, so we're 0, and 0, and 0, and 0, and 0, which means it's 0 ever after that. And so we have the final thing that says, oh, it's e to the lambda t, the identity, plus a minus lambda it. In other words, it's super easy to compute. This is nice. This is wonderful. And indeed, in some sense, I would say that when you're faced with the problem with repeated eigenvalues, the first thing you should do is, once you know you have repeated eigenvalues, compute e to the at. because once you have e to the at, you can say, well, what if I want to have the two solutions? Great. How do you find your two solutions? The columns. The columns are your solutions, right? Because that's what it is. Remember, e to the at is the fundamental matrix. And when you have a fundamental matrix, the columns correspond to solutions. What if you have initial values? Wonderful. Take e to the at and multiply it by your initial values, and life is good. And you got your answer. So now repeated eigenvalues are actually desirable in the terms of they're pretty fast to solve once we have them. All right, well, let's take a look at a few problems. An example. Find e to the at for a equals 2, 1, minus 4, 6, which has repeated eigenvalues 4, 4. Okay, so they're already telling us that we have repeated eigenvalues of 4, so we're going to skip computing the eigenvalues. We're not even going to touch finding the eigenvectors because we're after what? E to the at. So we say, all right, well, we have a formula. And we say the formula says e to the at is e to the lambda t times the identity plus a minus lambda I t, and stop. So let's fill in what we have. So e to the lambda, what's lambda? It's your eigenvalue. So that's e to the 4t, 1, 0, 0, 1. That's what the identity is. Plus a minus lambda I. So we're going to subtract 4 off the diagonal. So 2 minus 4 makes minus 2. 1 minus 4. 6 minus 4 makes a positive 2. T. Which is e to the 4t. And we'll go ahead and put these two together. And what do we have? Well, we'll have 1 minus 2t. 0 plus t. 0 minus 4t. And then 1 plus 2t. And done. We found e to the at. Okay, well, what else can we say? We mentioned we can find solutions. And so let's talk about x1, x2. So the moral is the first column gives x1, second column gives x2. So x1, don't forget this part out in front, e to the 4t, 1 minus 2t, minus 4t. x2, again, don't forget, e to the 4t, t, 1 plus 2t. And we're great. We have our two solutions. And so, again, repeated eigenvalues are friends. We like them. And what if we wanted some initial conditions? Let's look at an example with that. So in this example, we're asked to use matrix exponentials to solve for x and y of the following system. X prime is 5x plus 9y, and y prime is minus x minus y. Initial conditions are given. X of 0 is 5, y of 0 is 7. Now, see how it says matrix? So the first thing we should do is write this as a matrix problem. So we'll do that. So we'll have our x, y prime. We get our coefficients, 5, 9, minus 1, xy, which we'll abbreviate as z prime, equals, again, our matrix of coefficients, and z. All right, so let's figure out what's going on. The first thing we always do when we have a matrix problem is figure out the eigenvalues. All right, so what are these eigenvalues? Oh, okay, so 5 minus lambda, 9 minus 1 minus lambda. So this is our a minus lambda I. So that's our 5 minus lambda, minus 1 minus lambda, subtract minus 1 times 9. And we start multiplying now. We get minus 5 lambda, plus lambda squared. And here we'll get a plus 9. So that makes lambda squared minus 5 plus 1 is minus 4 lambda minus 5 plus 9 plus 4, which is lambda minus 2 squared, which means repeated eigenvalues. And now we're like, yeah, that's my jam. Woo! Yeah. So why? Because we have a nice tool. And when you have a nice tool, it's like, I'm going to use my tool. Okay, what's our tool? Well, matrix exponentials. So we say, okay, great. Now that we know our eigenvalue is 2, we can say that e to the at, well, that's e lambda t times the identity plus a minus lambda I t. Okay, well, now we just put in what we know. We know lambda, it's 2, and we know a, that's a, and everything else is common stuff. So that's e to the 2t. The identity, 1, 0, 0, 1, plus a minus lambda I, so we're going to subtract 2 off our diagonals. So we're going to have 5 minus 2, 3, 9, minus 1 minus 2 is minus 3 times t. All right, well, that's e to the 2t, and then we'll have 1 plus 3t, then we'll have 0 plus 9t, then we'll have 0 plus negative 1 times t, then we'll have 1 minus 3t. All right, so that's e to the at. Now, we want to solve for initial conditions, x of 0 equals 5, y of 0 equals 7. So what comes next? Well, we multiply e to the at times our initial conditions. So we say, all right, we have e to the at times x of 0. This will be the solution to the system. And, all right, well, in our case, we didn't use x, we used z, so okay, z of 0. What was z of 0? Well, we can come back. Remember, z is x and y. So x of 0 is 5, y of 0 is 7. So that tells us that what we have is we copy down our e to the at that we just found. 1 plus 3t, 9t minus t, 1 minus 3t, and then it's going to be 5, 7. All right, so that's e to the 2t. Then we're going to have 5 times 1 plus 3t, and then plus 7 times 9t. Then downstairs we'll have 5 times negative t, and then we'll have 7 times 1 minus 3t. And, okay, so what's that? Well, we have 5 plus 15t, and then 7 times 9, that's 63, 63t. And here we have 5 times minus t, that's minus 5t, then plus 7, and subtract 21t. And we say, okay, well, that makes e to the 2t. Well, we'll get 5, 15 plus 63 makes 78. Then here we have 7 minus 5 minus 21 makes minus 26. All right, so 78 and minus 26. Okay, and now that's our answer in terms of z. We started with x and y separated. So the last part is just to unravel. Say, okay, well, the top part is x, the bottom part is y, and so our answer is x is e to the 2t times 5 plus 78t. And y, well, that's e to the 2t times 7 minus 26t. And we're done. We're done. Now, you might say, that seemed like a lot of work. But remember how much we used to have to do. And you're like, you're right. This is better. It is the power of matrix exponentials. And we can even do more. So stay tuned. Lots of fun stuff coming up in the next few lectures. All right. That's it for today. Bye.